Welcome to the course on advanced machining processes. Today we are going to discuss on ultrasonic machining process. So this is the organization of my lecture. Okay. So first we shall discuss about that introduction of this ultrasonic machining, then working principle of ultrasonic machining process, then elements or components of ultrasonic machining experimental setup, and then parametric analysis, whatever parameters are there, then that effect of each parameter on the process performance we shall discuss, and then process capabilities and application of this process we shall discuss, and then we shall discuss about the material removal model. So there are different kinds of models are there for material removal. Okay, so we shall discuss the mathematical formulation of this ultrasonic machining process for material removal. Okay, so first we have to know what is ultrasonics. Okay, so when there is a vibrating waves having frequency greater than the upper frequency limit of human ear, then it is called a ultrasonic frequency. So basically that limit of human ear is 16 kilohertz or 16,000 hertz. Okay, so when this frequency of vibration is more than 16 kilohertz, then we can call that vibration as ultrasonic frequency. Okay, so there are two types of frequency waves. There are two types of waves. One is longitudinal wave and another one is the shear wave. So longitudinal wave, we generally use longitudinal wave for machining purpose in case of ultrasonic machining process. So there are shear waves also there. So in case of ultrasonic machining process, we generally neglect the shear wave. Okay, so longitudinal waves is used for ultrasonics, and this kind of longitudinal wave it can easily propagate in solids, liquids, and also in gases. So what is longitudinal magnetostriction? Okay, so this magnetostriction or this kind of longitudinal wave can be generated by magnetostrictive type transducer. Okay, so what is longitudinal magnetostriction? If a ferromagnetic material is placed in a continuously changing magnetic field, so it results in a change in length of the transducer. Okay, so suppose there is a change in magnetic field and we are putting on one ferromagnetic material inside that continuously changing magnetic field, there is a change in length of that material. Okay, so as we are giving a very high frequency of this current, okay, so for changing that magnetic field, so it will generate high frequency vibrating wave, so longitudinal wave. Okay, so that high frequency wave we can use or utilize for machining purposes. Okay, so there are different kinds of materials which can give ferromagnetic materials which can generate this kind of or suitable for this magnetostriction type transducer. So one kind of material is nickel, another one is the permalloy. So because it is basically alloy, okay, it consists of 40% nickel, 55% iron. Okay, another material is the permanganate, which consists of 49% cobalt, 49% iron, and 2% vanadium. Okay, so these materials are made of laminated sheets. Why you are using these laminated sheets? Because we are using AC current. Okay, so in case of AC current, there is a eddy currents are generated. So to reduce that losses due to the eddy current, so these materials are actually made of laminated sheets. Okay, so what is ultrasonic transducer? Ultrasonic transducer, it converts any kind of form of energy into the ultrasonic waves. So electrical energy, it may be electrical energy. Okay, so electrical energy, it is converted into the mechanical energy, that is a high frequency vibration. So in case of magnetostrictive type transducer, that electrical energy is converted to the high frequency mechanical vibration. Okay, so what is the working of ultrasonic machining system? So there is a AC power supply, which AC power supply. Okay, so this AC power supply is connected to the ultrasonic waves generator. So this ultrasonic wave generators, it takes power from a AC power supply, then it is connected to a ultrasonic transducer. Okay, then it is connected to a tool concentrator or tool horn, and then tool concentrator is connected to a tool, and then this tool is connected to a vibrating abrasives. So just below the tool, these abrasive particles are there inside the slurry. Okay, and then these vibrating abrasives these abrasive particles hit the workpiece surface, and because of this kinetic energy gained by these abrasive particles and due to the hammering action of these abrasive particles, so there is a tiny chips are generated from the workpiece surface. So thousands of craters are formed on the workpiece surface, and we can get the replica of the tool to be produced. Now this is the schematic diagram of ultrasonic machining process. Okay, so now here you can see this is the transducer winding. Okay, so here this is the transducer winding is there. Okay, so inside there is a ferromagnetic material or ferromagnetic material is there. Okay, so when we are giving a high frequency current, okay, so this high frequency current is generated in the ultrasonic wave generator. So this ultrasonic wave generator, this work of this ultrasonic wave generator is that it takes current power supply from it takes the power supply and generate high frequency waves. Okay, so high frequency current it generates. Okay, so this is the these coils actually high frequency currents are passing through these coils, and because of this this ferromagnetic material, there is a change in magnetic field in the ferromagnetic material, and its length is changing. Okay, so this coefficient of ultrasonic coefficient is E epsilon. Epsilon is del L by L, where del L is the changing length of the magnetostrictive material, and length is L is the total length of that magnetostrictive material. So now this transducer, it is connected to a concentrator. Okay, so now this concentrator is connected to a tool holder, and then this tool holder it is connected to a tool. So this is the tool here, and this is the nozzle which is supplying the slurry in between this tool and this workpiece. So this is the nozzle here. Here we are using it is shown in cylindrical nozzle is shown here, and in between this tool and workpiece this slurry is supplied by this nozzle, and this slurry consists of this water. Okay, generally water is used as a slurry, and these abrasive particles of different sizes, abrasive particles are mixed with this slurry. Okay, so here this is the gap between this tool and the workpiece. So this gap is generated because this slurry it is provided by the nozzle here. Okay, so through this nozzle slurry is provided, and there should be a gap between the tool and workpiece for that slurry to come outside the working zone or machine zone. Okay, so this is the total experimental setup of the ultrasonic machining process. Here you can see this the concentrator is used. Why this concentrator is used? Because whatever this transducer is generating this amplitude, it is not sufficient enough to machine the workpiece surface. That's why it is connected to a concentrator. So this working principle means working of this concentrator is that it amplifies the amplitude of vibration of whatever transducer is generating. Okay. So this concentrator has to be vibrated with a this concentrator has to be vibrated with a natural frequency of the system. Okay, so now working principle of this ultrasonic machining process. So that is the electric energy of high frequency is converted into a mechanical vibration through a transducer. So still now we have discussed this magnetostrictive type transducer. So this mechanical vibration is transmitted to the abrasive particles in the slurry via energy focusing device or horn or concentrator or tool assembly, and these abrasive particles just below the tool actually it gains the kinetic energy. Okay, so that is a this tool is vibrating with a very high frequency. Okay, so it is more than 16 kilohertz. Okay, so now just below the tool that is a slurry is there. This slurry consists of abrasive particles. Because this transducer this tool is vibrating with a very high frequency, these abrasive particles are just below the tool. Okay, so it is hit by this tool. These abrasive particles is hit by the tool, and these abrasive particles gain kinetic energy, which is equal to the half mv square, where m is the mass of these abrasive particles and b is the velocity of these abrasive particles. Okay, so because of this kinetic energy is gained, these abrasive particles, after getting this kinetic energy, it may hit another abrasive particle or it may directly hit the workpiece surface. Okay, so one more thing we want to say here, this ultrasonic machining process, it is suitable for very brittle and hard material. Brittle and hard material. So when these abrasive particles are hitting the workpiece surface, this material is removed by the brittle fracture from the workpiece surface. So each and every tiny abrasive particles which are hitting the workpiece surface, this material is removed by the brittle fracture, and tiny chips are actually generated from the workpiece surface. Very small tiny chips are generated from the workpiece surface. Now you consider there is a tool, it is a bigger diameter, just below the tool so many abrasive particles are there, and this tool is vibrating with a very high frequency, so 16,000 kilohertz, 16,000 times per second. So how many attacks are there by the abrasive particle on the workpiece surface? So there are thousands of attacks per second by these abrasive particles. Because of this kinetic energy of these abrasive particles, it will hit, and these tiny chips will be generated, and after some time it will take the shape of the tool. Okay, so this workpiece surface will take the shape of the tool. So this tool should be the replica of the workpiece to be made on the workpiece surface. So any kind of complex geometrical shape can be generated, or it may generate through holes, or it may generate blind holes. It may be cylindrical hole, it may be square hole. Okay, any kind of things can be done by this ultrasonic machining process. Okay, so it is very popular among the advanced machining process, where this tool is workpiece is very hard material and workpiece is very fragile material. Okay, suppose we are machining glass, or we are machining quartz. So okay, so if we do this machining operation on a grinding operation, or you can do this drilling operation in a drilling machine or in a milling machine. So suppose this glass is there, so glass immediately it will break if we use any drilling machine or milling machine, or if you want to polish, if we do on a grinding machine, immediately there will be cracks will be generated. Okay, so because these are very fragile material and very brittle material. So that's why we need to have a very small forces. Now in this case, as the abrasive particles are not touching, this tool is not touching to the workpiece surface directly. Okay, so this energy is transmitted via these abrasive particles. Okay, so nowhere this tool is touching to the workpiece surface. So this force coming through the individual abrasive particle is very less. Okay, so that's why this process is very good for brittle material, fragile material, and very thin section of materials. So there are two types of transducers are there. Okay, so now we understood what is transducer. This transducer it converts any kind of energy into the mechanical energy. So in our case, it is converting high frequency electrical energy. Okay, so through this ultrasonic wave generator. Okay, so it is converting this electric energy, high frequency electric energy, into a mechanical vibration. There are two types of transducers are there. One is the magnetostrictive type, another one is the piezoelectric transducer. In both the systems generate high frequency vibration. Okay, so magnetostrictive type already we have discussed how it is generated. So in magnetostrictive type, its efficiency is very less. Okay, so because most of the energy is utilized for the heating. Okay, so it generates lots of heat because its efficiency is low. So rest of the things energy is means it is wasted because of heating. So that's why we have to use some cooling system to release the heat from the transducer. So it has a low efficiency, but it can generate high power capacity. Okay, so that's why when we need very high power capacity, we can use this kind of magnetostrictive type transducer. Another one is the piezoelectric type transducer. So all we know. So its efficiency is very high. So that's why we don't need any cooling arrangement, and that's why it does not have any heat damage liability, but its power capacity is very less. So piezoelectric transducer like subsquares. So if we pass a current through this piezoelectric material, it expands. And the reverse thing is that if we compress this piezoelectric material, it generates currents. So we are using the opposite thing. Okay. So when some electrical energy is passing, okay, so this piezoelectric material will expand. Okay, so this concept of this piezoelectric material is utilized for generating high frequency vibrated wave. Okay, so there are different kinds of force or illusion, different kinds of models are there for material removal. So first one is the illusion model, which is called model A. Second one is the colliding or sliding model, sliding of abrasive model, that is model B. And third one is the small scale removal action by exciting abrasive. Okay, so that is called model C. So in model A, illusion model, the size or diameter of the craters which are generated, it is 0.5 to 5 micron. Okay, so it is quite high. And for this colliding or sliding abrasive mode or model B, mode B, so the size of the craters generated is 0.3 to 1.5 micron. And for the small scale removal action, the size of the craters are generated, this is 40 to 60 nanometer, which is very less. And depth of the crater which is generated into the workpiece surface by each abrasive particle, in case of illusion model it is 0.5 to 1 micron, and in case of colliding or sliding of abrasive or mode B, it is 0.01 to 0.3 micron, and in case of small scale removal action, okay, so it is in mode C, it is 3 to 6 nanometer. So shape of the geometry of the surface generated in case of mode A, it is, or craters, geometry of the craters generated, it is in the round marks. And for colliding or sliding or mode B, it is irregular shaped marks or weight shaped pits or sketches. And in case of mode C, it is nanoscale marks. So this information is taken from this reference material symbol mechanism in non-contact ultrasonic abrasive machining process by Y. Aichia et al., which is published in WIR, that is an international journal. Okay, so there are different modes are explained in this slide, also in the next slide. So this one is the mode C or small scale removal of the process. So these are the abrasive particles which is hitting due to the ultrasonic generator, or which is tool which is vibrating with the ultrasonic vibration. So this is the direction, longitudinal direction of this vibration. So this is the acoustic streaming of this wave along this longitudinal direction. So because of heating by this ultrasonic means this tool, these abrasive particles are coming towards the workpiece surface, and it will make these tiny small chips on the workpiece surface. So these are the processing marks. So these are the exciting abrasive particles. Okay, so small scale removal process is shown here. So in the next slide, all the three modes. So in this slide, all the three modes actually it is shown. So this is the first mode here. So which is in mode C here because of this exciting abrasive. Okay, small scale removal action here, almost spherical shape is generated on the workpiece surface. Now this is the mode B, and mode A is shown here. So this is shown. This is due to the cavitation effect. Okay, so cavitation effect is there because it is vibrating. This tool is vibrating with a very high frequency. Okay, so there may be volume or pressure may be created just below the tool here. So here pressure may be created when these bubbles actually collapse. Okay, so then these abrasive particles it moves with a very high velocity because of this collapse of these bubbles. Okay, there are two modes are there. So this is the one mode, this is colliding or sliding mode. Okay, so this is mode B, and here this is the mode A, this is the erosion mode by this cavitation effect. So now we have discussed there are three modes, that is the small scale mode, colliding mode, and this is the erosion mode. Okay, so in this erosion mode you can see bigger size craters are generated, and this colliding mode, medium size craters are generated, and in case of smaller scale removal, mode C, small scale removal is generated. Craters are generated from the workpiece. So now we have to discuss what are the different parameters of this ultrasonic machining process. Okay. So now we can think of this. The tool is the most important parameter. Okay. So this geometry of this tool should be the replica of this workpiece you want to generate on the workpiece surface. Okay. So tool is one of the main parameter. Machining parameter. Tool is one of the main parameter. Okay. So now slurry is the another parameter. Okay. Now workpiece is another parameter. Machine is another parameter, and tool holder is the another parameter. So these are the 5 parameters are there. So each parameter, it consists of several other parameters. So these are the 5 major parameters are there. So what is the performance characteristics of ultrasonic machining process? There are 4 performance characteristics or output of this ultrasonic machining process. So one is the material removal rate. Okay. So at which rate material is removed from the workpiece surface. Okay. So this material removal rate are 2 types of material removal rate is there. One is the penetration rate, that is in millimeter per second. Okay. So that is the in downward direction at which rate this hole is generated, and another one is the volumetric material removal rate. So how much volume of material is removed from the workpiece surface. So this unit is millimeter cube per second. Okay. So the first output parameter is material removal rate. Second output parameter is the tool wear rate. So tool wear rate is expressed as tool wear rate means because this tool is also hitting the abrasive particles, so there is a wear of this tool also there. So we want to minimize as less as possible, because if there is a high rate of wear of this tool, whatever abrasive particles are there, it may hit to another surface where we don't want any machining. So tool wear rate also one of the performance characteristics of this process. So cutting ratio or ratio of material removed by the workpiece by ratio of material removal rate from the tool. So material removal rate by that workpiece divided by material removal rate by the tool will give the cutting ratio. And surface finish, obviously it is a very good, it is a one of the main parameter. Okay. So high surface finish or means it is expected for means for any engineering applications of the components. Okay. So now this slurry, there are different sub parameters are there for this slurry. So first one is the feeding mechanism. So how we are feeding this slurry into the workpiece tool and workpiece cap. So one thing we have shown that slurry you can feed by side. Okay, through a nozzle we can provide slurry, or we can make a hole into the tool itself. Okay, so suppose the tool is, suppose it is a cylindrical tool, so we can make a hollow cylindrical tool, and through this hollow area we can provide the slurry into the tool and workpiece. Okay. Now volume fraction of the slurry. Okay, so this is another parameter. Temperature of the slurry is also another parameter. So temperature, actually because of this temperature, this viscosity of the slurry also changes. So that's why if viscosity changes, then it means its total property, slurry property changes. So temperature has to be maintained within a certain range. Okay, for getting efficient machining. So concentration of the slurry, that is also another parameter, and this slurry consists of abrasive particles also. So these abrasive particles type is also an important parameter. What are the different types of abrasive particles we are using? What is the grid size of these abrasive particles? And what is the liquid media or base media we are using for this slurry? And also viscosity of this media or slurry is also an important parameter. Now tool, what are the different parameters for this tool? This tool material is an important parameter. Then ductility of this tool material is an important parameter. So these tool material should be ductile. Okay. So because there is a machining is going on because of this brittle fracture on the workpiece surface, so it will take much more time for fracturing of the tool. So if it is made of this ductile material, and also finish of the tool also a very important thing. So surface finish also is important in case of this tool. Okay, geometry of this tool also very important. Okay, so we can do the tripping operation also. Suppose a bulk material has to be removed, so we can use, instead of a solid tool, we can use a hollow cylindrical tool also. Okay, so if we use this kind of hollow cylindrical tool and if it vibrates, so this circumferential area will be machined and total volume can be removed. Okay, so we are not removing the total volume, we are removing the circumferentially this hollow portion. Okay, in that hollow portion we are not doing machining, where these materials are there on the tool. Okay, so in that portion we are doing the machining operation. So another parameter is the workpiece. So type of material of this workpiece, hardness of this workpiece, strength of this workpiece, and thickness of this workpiece. So these things are actually matters. Harder material, it will take much more time, okay, for machining. Although this ultrasonic machining process also a very slow process, but if we machine very hard material, then it will take more time. Machine. So machine parameters are amplitude of vibration, at what vibration it is vibrating, and this frequency of this vibration, how many vibrations are there per second, that matters very much. And piezo type, what kind of piezo we are using. Also there is a static load is there, two static load. Okay, also there is a static load is there. And magnetostrictive power input, how much magnetostrictive power we are using. Okay. And tool holder, what is the material of this tool holder, what is the shape of this tool holder. Okay, that thing also matter. Okay, so what are the elements of this ultrasonic machining experimental setup? So first one is the sine wave generator, second one is the transducer, third one is the tool holder, fourth one is the materials of this tool holder, and fifth one is the tool, and sixth one is the abrasives. So these are the 6 components of this ultrasonic machining experimental setup. Okay, so we shall discuss one by one each of the components of this ultrasonic machining system. Okay, so sine wave generator, it converts, our line frequency is 60 Hz, 50 to 60 Hz. It converts low frequency or normal line frequency of this current with a high frequency current. So high frequency, it is more than 16 kilohertz. So this sine wave generator, it converts this 60 Hz frequency of current to high frequency current. Okay, so now this high frequency current is fed to the transducer. Okay, so piezoelectric crystals are there, or quartz. So it's two types of transducer already we have discussed. So if we consider this piezoelectric transducer, so suppose this is materials are quartz, so it can generate up to 900 watt, and its efficiency is 95%. And there are another kind of transducer we have discussed, that is magnetostrictive type transducer. It's generate 2.5 kilowatt and its efficiency is 20 to 30%. It is very low. So we need cooling system. Okay. So maximum amplitude of vibration is 25 micron in case of magnetostrictive type transducer. Now second one is the tool holder. So tool holder, I told that there is a concentrator is there. Okay. So this concentrator, it is used to amplify the amplitude of vibration from the transducer, because whatever transducer it is generating, it is very less. Okay. So that's why it should be connected to a concentrator. Okay. So suppose we don't need any concentrator, in that case we can use a cylindrical concentrator. Okay. Otherwise we can, if we want to get this amplification of this amplitude of vibration, in that case different kinds of methods are there. Okay, so different shapes are actually basically used, okay, for this concentrator. So tool holder, it may be amplifying type or non-amplifying type. So in case of amplifying, so its amplitude, it multiplies 10 times. So it tool holder actually it transmits the energy. So what are the different materials for the tool holder? Commonly used tool holder materials are monel, titanium, stainless steel. So these are the materials used for this tool holder. It has a very good acoustic properties, high resistance to fatigue, because this transducer, this concentrator, it is supposed to it is in an environment of with a very high frequency vibrations are there. So it can generate fatigue cracking. So to reduce that fatigue cracking, so this material should have resistant to the fatigue cracking. Okay, and that this tool holder should avoid welding between the tool holder and transducer. So as it is vibrating with a very high frequency, there is a chances that this transducer will weld or stick together or join together with the concentrator. Okay, so attach tool holder and with the transducer with a loose fitting screws. So that is the one mechanism. Okay, so monel is the very good material for this transducer. Okay, so have a high brazing and acoustic properties and used for low amplitude application. So for high amplitude application we need to have resistance for good fatigue strength, or it should have very good fatigue strength. So tool material, it should be very soft material. Okay, so generally mild steel, stainless steel, brass, these are the ductile materials are used for this tool material. So it should have high wear resistance. So surface condition for this tool should be good surface finish, and there should not be any scratches or scratch marks or machining marks on the tool, because if there is some scratches is there, abrasive particle will get hit by the scratches, and instead of vertically hitting to the workpiece, it will hit or reflect to some other places where we don't need any machining. We don't want any machining. Okay, so that's why this also, if there is a scratch marks are there, these scratch marks also can generate fatigue cracking there. It can generate cracks may be generated from that scratch marks. Okay, so tool design consideration are we have to consider for the overcut. So overcut is actually we cannot avoid overcut. Okay, so overcut is because of this. When tool is doing very means when you are doing the when we are doing the machining operation, then tool is fed towards the downward direction. So there is a tool feeding system is there, because every time we have to maintain the proper gap between the tool and the workpiece surface. Okay, so to maintain that we have to feed the tool towards the workpiece. Okay, so when it is fed towards the workpiece sufficiently enough to the bottom. Okay, so in that case what happens, there is a side wall, from the side wall of this tool also abrasive particles are hit, and it will cut, it will do the heating operation to the workpiece surface, and it will generate it will generate craters from the side walls also, or we can say that from the side walls also there is a, because of this transverse direction, these waves also do the machining operation. Okay, so there is a side cutting is there. So we have to reduce that side cutting as much as possible. So we have to consider this overcut and minimize. We have to minimize the fatigue problem by silver brazing of this tool and tool holder. By silver brazing of this tool and tool holder, we can reduce the fatigue cracking. So abrasives, different kinds of abrasives we can use. So here it is shown in the it is sorted with the means from lower hardness to the higher hardness. Okay, so aluminum oxide, this is the its hardness is lesser than other abrasive particles. Then more means silicon carbide has higher hardness than aluminum oxide. Then boron carbide, it is more harder than this silicon carbide. Okay, so in case of increasing hardness, it is shown here. Okay, so obviously this abrasive particle hardness should be higher than the workpiece material hardness. Then only it can hit the workpiece and there will be a brittle fracture. Otherwise, if hardness of these abrasive particles are lesser than the workpiece material, then it will not generate any crack from the workpiece surface. So selection criteria, what should be the selection criteria, which abrasive particles, because we have so many options are there, so many abrasive particles are available in the market, so which abrasive particles we should use. So it based on the hardness, size and life and cost of the workpiece material. Okay, and so we have to consider the what is the hardness of this, abrasive, size of this abrasive, life of the abrasive and cost of this abrasive we have to consider. Then workpiece material hardness also we have to consider. Suppose if it is very hard material like titanium, then we have to use this boron carbide. And desired material removal also an important. So we want material removal rate as high as possible, but at the same time we want very good surface finish. Okay, so if we want the material removal rate very high, in that case we have to consider harder abrasive particles. Okay, so desired material removal rate and surface finish of the workpiece material also governs the which abrasive particle we should choose. Low concentration of abrasive particles are used for default draining when length to diameter ratio of the hole. So what is the length and what is the diameter of this hole is very high. So L by D ratio, so it is called high aspect ratio of hole. When this L by D ratio is very high, so in that case we have to use low concentration of this slurry, or in low concentration of abrasive particles in the slurry, so that these abrasive particles should reach each and every where into the tool and workpiece, that gap it should be uniformly distributed. Okay. So process performance, material removal rate and surface finish. Okay. Grain size generally it is used 240 to 800 micron. Supply medium, what should be the base medium for this slurry? Water is the best medium is used. Okay, because of its low viscosity, it can pass to means in between the gap between the tool and workpiece. Okay, so other options for this base media is benzene, glycerol and etc. Okay, so now we have to do the parametric analysis. Okay, what are the effect of individual parameter? Okay, what is the effect of individual parameter that we have to do? So that's why we need to do this parametric analysis. Okay. So main machine parameters are amplitude of vibration and frequency of vibration. Okay. So amplitude of vibration and frequency of vibration are the main machining parameter. So we can control from the machine this amplitude of vibration and frequency of vibration. Okay. So this is the plot having between this penetration rate, it is millimeter parts second, or you can say this is the linear material removal rate. Okay, and with the amplitude of vibration. Now we can see if we increase the amplitude of vibration. Okay, so in that case, what happens? This abrasive particle will get higher energy or higher kinetic energy because of higher velocity. Okay, so if we increase the amplitude of vibration, your material removal rate will increase, but after some time, if you see after it reaches the optimum value, okay, it stabilizes. Okay, so it stabilizes after reaching to a certain value. So if you increase the pressure or load, then also your penetration rate also increases. Okay, with the amplitude of vibration. Okay, so initially penetration rate increases up to a certain value. Beyond the optimal amplitude of vibration, it tries to stabilize. Main reason being the constant force. So if we increase the amplitude of vibration, but whatever static load we are using, that is fixed. So that's why whatever static load is using, that is fixed. So that's why, okay, so if we increase the amplitude of vibration, still after some time, after optimum amplitude of vibration is achieved, so there is a stall or it will stabilize. So now frequency of vibration, if we increase the frequency of vibration, you can see, okay, so penetration rate or linear material removal increases. Frequency of vibration, if we increase the frequency of vibration, so then parts second, number of hitting by this abrasive particle increases. So more number of abrasive particles per unit time are hitting, because this tool is vibrating with a very high frequency. So more number of particles are taking part into the machining operation. So more craters are generated. So then this means this penetration rate increases. But after some time you see this penetration rate stabilizes. So as the frequency of vibration increases, penetration rate increases because of the more number of abrasive particles per unit time on the workpiece surface. But after it reaches the optimum frequency, then you can see that it stabilizes. Okay, it stalls when it reaches the optimum frequency of vibration. So grid size also affects the machining rate or penetration rate. Okay, with the increase in the grid size of these grids, okay, this penetration rate increases because bigger size abrasive particles hit and it generates higher higher volume of the chips, okay, or bigger volume of the chips. But if we increase the abrasive grid size, it reaches the optimum value, okay. But after some time, although we increase the grid size, then this machining rate decreases because energy, whatever this total energy per movement, okay, so it is fixed, okay. Force is fixed here, okay. So that's why whatever this energy, it is distributed among the abrasive particles, okay. So when these bigger size abrasive particles are there, now in that case there is a less less number of abrasive particles which is taking part into the machining, okay. So then in that case also there is a reduction in the penetration rate. So that the force is constant. So that's why at different grid size, okay. So with a bigger, although there is a bigger grid size, but force is constant, okay. So that's why this machining rate reduces. Okay, so this is the plot for tool wear rate. Relative tool wear rate means workpiece hardness divided by tool hardness will give the tool wear rate, okay. So here in y-axis, that is the material removal rate or penetration rate. Now if we increase the wear rate or workpiece hardness by tool hardness, okay. So if we increase the workpiece hardness, okay, obviously your machining rate will reduce, okay. Or if we increase the if we decrease the tool hardness, okay, so in that case also your material removal rate will reduce. So as the hardness ratio increases, the material removal rate decreases because penetration rate is a function of workpiece hardness. If tool hardness decreases, then the abrasive can penetrate inside the tool to reduce the penetration rate in the workpiece. Okay, so this particle velocity also take part into the machining. Okay, so higher the velocity of the particle, your machining rate will be higher because this kinetic energy whichever is gained by these abrasive particles, it is utilized for the machining. Okay, so this kinetic energy is half mv square. Okay, so this kinetic energy, so this particle velocity increases, this kinetic, because of this kinetic energy increases, so machining rate also increases. Okay, concentration of abrasive particles. Okay, so if we increase the more concentration of these abrasive particles, okay, so in that case machining rate or linear material removal rate increases, but it reaches to an optimum value. After that it slightly reduces or stabilizes. Okay, if we increase the concentration of these abrasive particles beyond a certain value, in that case whatever abrasive particles are there, they collide with each other. Okay, so they collide with each other. Okay, so collision with each other results in reduction in the machining velocity. So when concentration of this abrasive particle is too high, then lower impact velocity will be there. Because of this, it collide with each other. Okay, so here it shows the static load. So in the next slide we shall show how to give the static load. Okay, so the static load is constant for a certain for a single machining operation. For every experiment, the static load is constant. Okay, so now if we increase the static load, from one experiment to next experiment, if we increase the static load, in that case penetration rate also increase, but after some time, after it reaches the optimum value, then it reduces. Okay, so this is the relationship between static load and penetration rate shows an optimum value. So optimum penetration rate increases with the amplitude of vibration. Now if we increase the amplitude of vibration, then optimum penetration rate also means so so it increases. Okay, optimum static load, it increases with the increase in the amplitude of vibration. So here every curve, so we are varying the static load here, so here also static load, but here tool diameter actually increasing. Okay, tool diameter is increasing in the bottom direction, so here it is lower tool diameter, this one is the bottom bigger tool diameter. So with the lower tool diameter penetration rate is high, for bigger tool diameter this penetration rate is less. Okay, so increasing the tool diameter decreases the penetration rate. So here we are increasing the tool diameter, the penetration rate decreases. So because this pressure decreases, okay, so increasing the static load increases the total force acting on the slurry or the impact force acting on each abrasive grain. Static load can be increased by counterweight, pivoted counterweight, spring or pneumatic or hydraulic means. Okay, so next slide we shall see what are the different way we can give the static load. Okay, so this is one process for giving the static load to this tool. So this one is the counterweight is generating. By changing this counterweight, we can change the load given to the tool. So this one is the pivoted counterweight is used. So using this pivoted counterweight, we can give the load to the tool. So this one is the spring loaded system. So using different spring constant, okay, different kinds of spring with a constant of elasticity, different constant of elasticity. Okay, so we can change the tool, we can change the load on the tool. Okay, so now another way of giving load is pneumatic or hydraulic. Okay, so by using this pneumatic or hydraulic oil or hydraulic pressure, we can change the load, static load on the tool. So process capability is a very important thing. So what is the capability of the process? Okay, so what material? So it works fine for hard and brittle material because initially I told it because it brittle it makes a brittle fracture into the workpiece surface. So machining is going on by brittle fracture. So hardness in Richter scale, C scale. Okay, Rockwell hardness, HRC Rockwell hardness, it should be more than 40. Rockwell hardness in C scale, it should be 40. Okay, so this carbide, ceramics, tungsten, glass, these are the materials which are used for this as a work material. So surface finish achieved by this ultrasonic machining is 0.25 to 0.75 micron. Okay, so accuracy also is an important parameter. Okay, conicity of the drill hole is there. So you can see that after machining, this ultrasonic machining, if we are doing cylindrical hole, you can see this kind of conical shape of hole is generated because of this sidewall machining. Okay, so to reduce the conicity, we have to develop different kinds of mechanism. So one is the reverse shape of this tool. You can take the shape of this tool like this. Okay, reverse, so that it can reduce the sidewall machining should be reduced. Okay, can be reduced. So this is called negative taper, and higher static load on the tool. If we use higher static load, in that case also conicity can be reduced. Outer roundness of this hole. So outer roundness, we know outer roundness is, suppose a circular thing is there, so we can consider it as a pen. It is a circular cross section. Although in naked eye it is shown as a circular, but if you see under microscope or if we attach a probe there, one machine is available, so you can see this is not perfectly circular. So in that case, we can it is not perfectly circular. So in that case, there is a constant means in between this circumscribed and inscribed circle. This mean circle passes through this circumscribed and inscribed circle. Okay, so this gap between these two is called the outer roundness. So this outer roundness is a major issue. So in ultrasonic machining, this outer roundness is a major issue in case of ultrasonic machining. Okay, tolerances of these holes are generated plus minus 25 micron. So upper length of the depth of the tool, depth of the hole is generated as 51 millimeter. Even up to 150 millimeter in very special cases can be generated, and aspect ratio can be achieved up to 40:1, which is very high. So process applications. So this machining process can be used electrically conducting and non-conducting material. Okay, so any kind of material we can machine, but that material should be brittle and hard material so that there is a brittle fracture can be done. Okay, so hard and fragile components, very thin components, fragile components like glass, quartz can be machined by this process, which is not possible by conventional machining, any conventional relay or milling machine. Also, multiple holes can be generated by this process. Multiple holes can be generated. To increase the efficiency of this process, we can generate multiple holes. Thousands of holes can be generated by a single operation. So processing of silicon nitride turbine blades. So these turbine blades, there is a cooling channels are there. Okay, and some holes may be generated for fixing purpose. That can be done by this ultrasonic machining process. Glass, ceramic, titanium, tungsten, these kind of materials are machined. So drilling, profiling are done by this process. Can be used in conjunction with the ECM, EDM, ECG, electrochemical grinding. So we can use as a this one in conjunction of other process as a hybrid process. Okay. So thank you.